Swayam Prabha. Digital India. Educated India.
Okay, so let us try to see if we can wind up our discussion of non-equilibrium Green's function. So, remember that I told you that you see the point is that regardless of whether the system is in equilibrium, by that I mean the system has a Hamiltonian that is time independent, and it could possibly be coupled to some reservoir at some finite temperature, or it can be coupled to a reservoir which is not only at a finite temperature but also at some finite chemical potential. So, implying therefore that the system can exchange both particles and energy with the surroundings. So, if that is the case and even if that is not the case, even for a truly isolated system, the quantities of interest especially with respect to the one particle Green's function would necessarily be the particle and whole Green's functions, because after all that is all there is to it. You see, you either calculate this or you calculate the other thing. So, this corresponds to a particle Green's function, this would correspond to whole Green's function. So, the only difference is that you see this bracket has different meanings depending upon the situation. So, if the system is truly isolated, this bracket obviously means expectation value with respect to ground state. But if the system is not isolated, for example, if the system is a grand canonical a part of a grand canonical ensemble, that means the system is not only exchanging energy with surroundings, it is also exchanging particles with surroundings, so that it comes to an equilibrium with a chemical potential and temperature that is common to both the system and the surroundings. Then you see the average, the brackets here I am talking about for the particle and whole Green's function, they have a different meaning, namely it is not merely the expectation value, it is actually the trace over all possible states of the system with an appropriate weight, which is similar to the Boltzmann weight if it were merely canonical. So, it is basically e raised to minus beta h minus mu n, that is what it would be. So, it is basically it is a weighted average over all the states of the system, not merely the ground state. So, that is all you have to keep in mind, that basically that is the only difference between a truly isolated system versus a system that is in contact with some surroundings. So, the meaning of the brackets differ, but otherwise in both situations you are simply called upon to calculate either the particle Green's function or the whole Green's function, that is all there is to it. You see, if you are allowed to remove a particle or insert one particle or remove one particle, then after all that is the only thing you can calculate. Either you calculate the particle Green's function where you insert a particle first, or you calculate the whole Green's function where you remove a particle first. But the point is that you see that the fact that there are two different such Green's functions that you have to calculate becomes inconvenient when you are trying to solve. See, if your Hamiltonian typically will be not exactly diagonalizable for various reasons, and the most serious reason being that particles interact amongst themselves. Not only do they interact with possible external fields, but they also interact amongst themselves. So, when they interact amongst themselves, the implication is that you won't be able to handle it. So, you will have to expand in powers of that interaction between particles. So, when you do that, you will necessarily be called upon to perform a perturbation series expansion. Now, when you do that, the problem is that it is not that much of a problem, it is just an annoyance. The fact that you have two different Green's function that you have to perturb and find the series expansion for is somewhat irritating. But there is a more, I mean, there is a deeper reason for why it is desirable to have a kind of a single definition for a Green's function which results in these two particle and whole Green's function as special cases. So, the reason for seeking a more compact definition of the one particle Green's function is because that compact definition will actually then obey an exact equation even when interactions are present. So, and it will only involve that Green's function and nothing else. See, right now if you try to write down the equation of motion for the particle Green's function, for example, you will soon find that because the particles interact amongst themselves, the equation of motion for the particle Green's function will start to involve a Green's function where you are going to be creating two particles and annihilating two particles. So, the one particle Green's function, the equation of motion for the one particle Green's function will involve two particle Green's function, and the equation of motion for the two particle Green's function will involve three particle Green's function, and so on and so forth, and endlessly, and that is of course not convenient. So, it is better to see if there is some way in which you can have a situation where the equation of motion for the one particle Green's function will involve only the one particle Green's function and not anything else. So, so if you want to achieve that goal, it is not going to be possible if you do the naive thing or the obvious thing, which is deal with this particle and whole Green's functions separately. So, it is important in that case to be clever about it. So, that means we are now going to introduce a well, I have already introduced that definition. It is basically called the time ordered Green's function. So, the time ordered Green's function, specifically especially if you have non-equilibrium external fields, then what happens is that you are called upon to define them in this peculiar way. So, the idea is that if so the time ordered Green's function is so this C is called the Keldysh contour. So, what you are staring at here is called the Keldysh contour. So, in the Keldysh contour the times that I am referring to here, T1 and T2, they basically live on one of these branches. So, in the implication is that if suppose T2 is here on this branch, this is called the lower branch, that is called the upper branch for obvious reasons. So, this is upper and this is lower. So, if T2 is on the lower branch, regardless of where T1 is on the, so long as it is on the upper branch, it does not matter where T1 is, T2 is always greater than T1. So, if T2 is on the lower branch and T1 is on the upper branch, it does not matter what the relative magnitudes of T1 and T2 are. Okay. So, T2 will always be greater than T1. So, whereas if both T1 and T2 are on the same branch, then T2 is said to be greater than T1 if it is numerically greater than T1 and they are both on the upper branch. But T2 T2 is greater than T1 if it is to the left of T1 if it is on the lower branch. So, basically on the upper branch T2 is greater than T1 if it is to the right of T1. So, the implication is that you are going like this. So, the path of increasing times is like this. So, this time is greater than this time is greater than this. So, this is always greater, this is greater, even greater, even greater, even greater, even greater, like that. So, you are going like this. So, this is increasing times, time is increasing like this. So, this is called the Keldysh contour. So, if you decide that your times are in this defined in this peculiar way, and then having done that you can always freeze the times to some numerical values. So, then what happens is that you see you will end up getting all these particle and whole Green's functions. So, suppose you want to you do not care about this contour ordered Green's function, you just want to extract say the particle Green's function. All you do is simply put T2 on the lower branch, T1 on the upper branch, and you got your particle Green's function. So, if you want the reverse, you want a whole Green's function. So, you see if I put T1 on the upper branch, it is going to be to the left of so time ordering means if T1 is greater than T2 in the sense of this contour. So, if T1 is greater than T2 on the contour, this is basically psi of x1 T1 psi dagger x2 T2 if T1 is greater than T2 on the contour, and it is plus or minus the other way psi dagger x2 T2 psi x1 T1 if T2 is greater than T1, plus minus depending upon whether it is boson or fermion. So, you see this is particle Green's function, this is whole Green's function. So, this is on the contour. So, if you really so all you have to do is if you want to get particle Green's function, all you have to do is make sure that T1 is on the lower branch and T2 is on the upper branch, and regardless of the numerical values of T1 and T2, you will always be studying the particle Green's function. And suppose you want the whole Green's function, you make sure that T2 is on the lower branch and T1 is on the upper branch, and regardless of now the numerical values. So, T2 can be as negative or as positive as it wants, and independently T1 can be anything. So, the point is once T2 is on the lower branch, you will always be studying the whole Green's function so long as T1 is on the upper branch. So, now if both are on the same branch, then you will be getting your usual time ordering. So, if both are on the upper branch, you will get time ordering in the sense in which you normally expect. If numerically T2 is larger, then you will get a whole Green's function, and if numerically T1 is larger, you will get the particle Green's function. Yeah, am I saying that right? So, if numerically T1 is larger, then this will be on the left and this will be on the right. Yeah, so then you will get the particle Green's function, and numerically T2 is larger, T2 will come to the left and you will make it the whole Green's function. So, if T1 and T2 are on the upper branch, the ordering is same as the numerical ordering, whichever is numerically larger is also larger in the sense of time ordering. So, in time ordering means that time ordering of A bracket T and B bracket T dash is same as A into B. If T is greater than T dash, it is B into A if T dash is greater than T, but that greater and lesser have different meanings depending upon the situation. So, if the times are on two different branches, I told you what it is. If they are on the same branch, it is the same as numerical ordering if both are on the upper branch, and it is the anti-numerical ordering if they are on the lower branch. That by that I mean, if T1 is greater than T2 numerically, it will be regarded as this T1 will be regarded as the smaller quantity if both are on the lower branch. See, so the numerical smallness will be the contour largeness if they are on both are on the lower branch, But if both are on the upper branch, then the numerical largeness is same as contour largeness. So if they are on different branches, then the lower branch is always larger than the upper branch. Okay, so that's all there is to it. So that is the Keldysh contour. So you might think that why are we making a simple situation complicated? Because after all, we had a particle Green's function, a whole Green's function. So we could have simply lived with two different Green's functions. So we are struggling to somehow combine these two Green's function into one contour ordered Green's function. It's not at all clear that that is worth the effort, because it seems like a lot of effort. So you will see that it is useful, because you see in the end what will happen is that if you decide to define contour ordering in this way, then you can write down your contour order Green's function in the grand canonical ensemble in this way, and then this is your S matrix with respect to. So if your fields evolve according to the part of the Hamiltonian that's independent of time, the part of the Hamiltonian that depends on time can be absorbed into this S matrix, and this S matrix is nothing but that part of the Hamiltonian which depends on time, and it's again along the contour. So now see, when you do perturbation series in this interaction term, so what this is going to do is that it's basically gives you a whole bunch of terms, and so there will be a whole bunch of terms in the denominator as well, but the point is that they will systematically cancel out the terms in the numerator where the fields actually couple. So in other words, that this is same as just doing the numerator expansion, but keep remembering to throw away terms where these two get coupled. So yeah, I know that I haven't spent enough time explaining to you how the perturbation series is supposed to be carried out. So the idea is that, you see, the point is that when when you turn off this external fields, then typically what will happen is that there is something called Wick's theorem which is applicable. So Wick's theorem simply says that if you want to calculate the average of A, B, C, D, so this is same as calculating the average of A into B times C into D, or calculating average of A into C plus B into D, like that. So it's like all sorts of pairings. So it basically says that's what it says. So if mutual interactions between particles are absent, then Wick's theorem is applicable. So that means so whether it is 4 or 6 or 8 or whatever it is, because that's what will happen here. So if this is, for example, the interaction between particles, it will involve density. So it will be a 4 fermion interaction. You will have psi dagger, psi psi, and you will get these types of terms, and they will all pair like this. So and one of those pairings will involve pairing these two, but and so once you pair up these two and take the average, it becomes some number and goes outside, and then you will end up having to deal with only the operators that are sitting inside S. But the whole point is that that will exactly cancel the terms coming from the denominator. So even though superficially it seems like we haven't really achieved the sort of goal that we set out to achieve in the beginning, namely that we wanted the S matrix to appear exactly in one place, but it looks like there it still appears in two places. But now you see that is only superficially so, because what this means is this is just a shorthand for saying that even though it superficially appears in two places, the implication is that when you do a perturbation series, the terms in the numerator that correspond to coupling of the psi and psi dagger are to be consciously omitted while performing the expansion. So once you remember to consciously omit the terms that correspond to coupling of psi and psi dagger, then you simply can afford to ignore this denominator entirely. So then my original claim is then valid. So that means the original claim was that this way of doing this way of defining Green's function will only involve S matrix in one place, namely in the numerator. So, but that is true so long as you remember to omit terms which in this expansion, in the perturbation expansion, you omit terms which involve pairing psi and psi dagger. So, if you omit those terms, then even though superficially it appears that the S matrix is there in both places, numerator and denominator, it is practically it's there only in the numerator. Okay, so yeah, so if you are having trouble understanding these issues, firstly I don't blame you, because it's a lot of there's a lot of details that I have either omitted or implied and not explicitly worked out everything. So that is something that as a student you have to try on your own, and if you are simply unable to understand what I am talking about, you really should be reaching out to me by email or asking me questions, and saying that, look, I don't know what you are talking about, explain it to me a little better. But try and understand whatever I have explained till now as much as possible. So whatever is remaining I can explain to you separately through email and that sort of thing, or your live sessions. But yesterday I had a live session. I was somewhat disappointed because I expected very specific technical questions, but most of you did not come prepared to ask me specific technical questions. So please come prepared to ask me specific technical questions next time. Okay, so the whole point is that this, so one goal has been achieved, namely that this way of defining the Green's function through this contour ordering in this grand canonical sort of ensemble picture achieves this goal of ensuring that the perturbation series is done in a clean economical way, namely that you simply only expand one of the S matrices in the numerator perturbatively, and then you start using your Wick's theorem and pair up all the terms. But there is a deeper, more a better reason for introducing this definition, this peculiar way of defining Green's functions through contour ordering. And that deeper, more convincing reason is because you can now derive a kind of an equation. It's called a functional differential equation. So it's not the sort of differential equation that you're accustomed to, but it's a kind of equation that I think even mathematicians seldom encounter in their own research. But it's one of those peculiar equations which involves both conventional partial derivatives as well as functional derivatives, the sort of functional differentiation and integration I've been discussing in the last few lectures. So it involves both those equations. But the important benefit to thinking this way is that the equation, such a functional differential equation for this contour ordered Green's function of this 10.103 will be such that it will only involve this Green's function back again. It won't involve anything else. So in other words, see, if you don't do it this way, if you insist on using your conventional, the original naive, and even, well, it's physically well motivated but technically naive definition of particle and Green's function as simply the average of psi and psi dagger, or average of psi dagger and psi. Even though that is physically well motivated, it is technically naive, because the equation of motion for those will involve now 4-point functions. That means those are 2-point functions, they will involve 4-point functions, and then if you then go ahead and try to see what equations those 4-point functions will obey, they will now involve 6-point function, etc., endlessly, and that is not a desirable situation. So you see so we have to be technically clever also. So we have to define the Green's function in a technically clever way, so that the equation that you write down for that Green's function will not involve anything other than versions of itself. So that is precisely what the Schwinger-Dyson equation is. Basically, it's an equation, it's a functional differential equation of the Green's function which involves other versions of itself. Okay, so how do you do that? So you do that by first let us see what is the system we are trying to study. So the system we are trying to study is the following. I want to study this system. What is this system? This is the usual kinetic energy, but this will involve 4 fermions. You see, this is usually C dagger. C is just kinetic energy, but this involves, this is the density of particles sitting at r dash, and this is the density of particle r, and so in some sense it is basically the interaction of particles sitting at r and r dash, and this is the mutual interaction potential energy, and this half is there because you are counting it twice and you want to count only once. Bottom line is that this is really what I want to study, a collection of quantum particles that are mutually interacting by a 2-body pairwise potential called V of r minus r dash. So I want to find the Green's function of such a system, that is particle and whole Green's function. So the way I am going to do this is, in order for me to derive an equation for that Green's function which does not involve anything but other versions of that Green's function, I will be forced to introduce an external time dependent potential. So now I am, see, because this is merely a device to generate basically it is a device to write down those Green's functions, write down those functional differential equations, then it is clear that I am at liberty to choose this external time dependent field according to my convenience, because after all in the end I intend to set it equal to 0, because really speaking it is not there. The system is in equilibrium, and so I am introducing it because I want to derive a functional differential equation for the Green's function which will involve this external time dependent field which will finally go away. But because it will finally go away and it is not really there, I am putting it in for my own technical convenience. I am completely at liberty to choose its properties. So specifically I am going to postulate that this time dependent external potential u of r comma t is such that the times involved are also along the imaginary axis. Now I am no longer going to be studying this Keldysh contour, because see, the Keldysh contour is useful when you have actual time dependent fields which are time varying in real time. But this is some mathematical device which I am introducing. So because it is a mathematical device, I can pretend that this time dependent external source also is meaningful only on the imaginary axis, and it is defined for times between t equal to 0 and t equals minus beta h bar. Okay. So physicists have this instinctive habit of setting h bar equals 1. I occasionally slip up and forget the h bar, because in other places I have written h bar. Okay, so the point is that yeah, so that's how I choose to introduce this external device, this external field which is actually not there, but I introduce it for my convenience and I'll finally get rid of it. So now the question is, if I decide that now this is my compiled Hamiltonian, which now involves both the external field as well as the field which involves as well as the kinetic energy of the particles and the mutual interaction potential energy. Now I can go ahead and ask myself, what is the equation of motion obeyed by the time dependent annihilation operator. So clearly it's going to be this. See, whereas the part of the Hamiltonian that evolves only according to the time independent part of the Hamiltonian will clearly obey this equation, right. So the implication is that these two are related through this sort of S matrix. Okay, so if your external field was 0, these two would coincide, because if u was 0, that these two are the same things. So the hat refers to the time evolution purely with respect to the time independent part of the Hamiltonian. So I have spent some effort trying to convince you that things work out, I mean that they are mutually consistent and so on. So I am going to skip that. Those are for some, I mean for those of you who are not entirely convinced by some of these steps, but they are not terribly important. So let us proceed. So the point is that this is the Green's function that I am going to be dealing with. Okay, so let me go all the way here. Yeah, so this is the Green's function I am going to be dealing with. So this, see this one notation 1 is a compact way of writing x1 comma t1. Okay, so this is called Kadanoff-Baim notation. So this was notation was invented by the well-known physicists Kadanoff and Baim in the early 60s, when they wrote this textbook called Quantum Statistical Mechanics. So that's where I learned all this from. Okay, point is that there are these. So again, I instinctively forgot my h bar. So the bottom line is that this Green's function, which is now defined, remember that the time ordering is now still on the imaginary axis. So all these times t1, t2, they all live on the imaginary axis between t equal to 0 and t equals minus I beta h bar. So this is clearly the equation of motion. That means the equation, the time evolution equation obeyed by this Green's function. See, the thing is that the reason why we have chosen to introduce this external source is, I mean, initially it seems like a unnecessary complication, because after all we are only interested in studying the system at equilibrium, but a system where the particles perhaps are in contact with surroundings at some temperature, but more importantly they interact amongst themselves, but they are still in equilibrium. So that means that there is the Green's functions look the same if you decide to shift the origin of your time to somewhere else, and they are also spatially homogeneous. That means that if you shift the origin of your coordinate system spatially, also the Green's function look the same. So there is spatial and time homogeneity as well. So that means the system is in equilibrium. So if it's in equilibrium, it's kind of annoying to introduce some external potential now that spoils all that nice equilibrium property. But you will see that it's important to do this, because the term that involves interactions between particles can now be written. You see this, what is this term that involves the interaction between particles? It involves 4 fermions. There are 2 creation and 2 annihilations. whereas this Green's function involves one creation and one annihilation, because that's how we defined it somewhere here. So it was defined like this. So it involves one creation and one annihilation. Okay. So these two are the same. This is the this is a S matrix perturbation series friendly version of this. So this is the original average that I am looking. So this is along the time ordering is along the imaginary axis, remember. So this time ordering is along this imaginary axis. So this is the original definition. Now I replace the C's by C hats, and this is kind of the same as, this is mathematically the same. That's what I have done in all these steps. This theorem basically shows that this is same as this, and this is basically involves the part of the Hamiltonian. This is the interaction picture. It only involves part of the Hamiltonian that doesn't change with time. The part that does change with time is lumped into this S matrix. So bottom line is that whatever this Green's function is, it involves one creation, one annihilation operator. However, its equation of motion now unfortunately seems to involve two creation and two annihilation. Now if you go ahead and write down the equation of motion for this, it will involve three creation and three annihilation, and so on and so forth endlessly, and that's where you're stuck, because then you don't have a convenient equation that you can solve. So the whole point of introducing this device of an external time dependent source is to see if you can go ahead and now express this term, which involves two annihilation, two creation, purely in terms of a Green's function that has only one annihilation, one creation. So in fact, I'll show you in the next class that it is possible to do that. So if I am successful in showing you that, then what this equation becomes is basically, it becomes an equation involving a version of the Green's function which creates only one particle and annihilates only one particle and nothing else. It doesn't involve Green's functions where you are annihilating two particles or creating two particles. So I'm going to stop here, and in the next class I'm going to continue and prove this important claim that the terms which I have written down here, which involve creating and annihilating two particles that correspond to interactions between particles, can now be expressed purely in terms of the Green's function involving one particle, so long as I involve the sources that I have artificially introduced into the problem. Okay, I am going to stop here, and in the next class let us continue. Thank you.